and also a professor at MIT. And today what I'm going to do is actually talk to you about running machine learning algorithms in the real world, and in particular issues that have to do with the design of our hardware and software for machine learning. And so everything that I say today, I'm going to do a bunch of calculations for you. And of course, as you can see, you should take everything I say with a grain of salt. So with that, I'm going to just jump right in. You're looking at a photo, and most of you can tell that this is Mount Fuji, and that takes you about 1/100th of a second to do. So neural tissue, that thing between your ears, enables you to do that, to actually recognize images extremely fast, right? Now, what is this neural tissue? Well, you know, anyone who's read popular science knows that, you know, our brains are made, you know, of neurons, and these neurons are interconnected among each other, and they have this kind of firing pattern. And from this image of neurons, you might kind of think that they are kind of far and dispersed, right? This is an image taken by Santiago Ramon y Cajal about 100 years ago. Today, we kind of know how to actually map neurons in a much more accurate way. And here's an example of what I'm showing you here is a penny, and on it is a little grain of salt, okay? And here are two neurons that sit in a volume that is about 100,000th of that grain of salt, okay? And what you see here are two apical dendrites in the brain. These are kind of parts of the receptive piece of a neuron, okay? And these little tiny slivers of brain, okay, you can, if you look at them, okay, around them, okay, around these two dendrites are sitting many other dendrites and many other axons and many other glia cells. So this whole volume, okay, this whole volume of you know, everything that sits around you know, a neuron is extremely dense. In fact, in that little grain of salt, there are about 100,000 probably neurons and about 1 billion connections, synapses between them. So extremely dense in what it looks like, but really the question is, you know, if we take this kind of what we know about from neurobiology and translate it to machine learning, right? Then, you know, the idea has been in recent years that deep learning is essentially, you know, we take the fundamental structure of neurons, right, and we translate it into something artificial. And of course, this could, you know, we're evolving in a different kind of evolutionary path with machine learning, but we started out with kind of the ideas that we would be mimicking neurons. And I'd like to kind of examine that idea, the idea that, you know, we started out trying to mimic the brain, and the question is, are we still mimicking the brain? Are we doing things that are anywhere close to what the brain does? Okay? And so with that kind of idea, I'd like to examine, you know, the hardware that we're building for machine learning right now, okay? And in some sense, we're being kind of sold the idea that the hardware we're building is neuromorphic, right? We need the term used by many people in the field is throughput computing. Machine learning is a throughput computing problem. Like the brain, it's extremely compute intense, and we've got to have specialized hardware to run it, because conventional CPUs are essentially, you know, they're not throughput machines, and we need these throughput machines. Okay, and it's a huge market that's being created for hardware for machine learning, starting with NVIDIA that makes GPUs, through Google that makes GPUs. Intel has a new product. It purchased a company called Habana that makes an accelerator. And there are 70 different startups that are making these kinds of hardware accelerators. Now, what do they look like, these hardware accelerators? Well, a typical GPU has thousands of cores, okay? It has, it has this high bandwidth memory, okay? And what it does, right, it brings the data and a description of your neural network into the memory of the GPU, and then applies, something on the order of 100 teraops per second onto this network and this data to actually give you, an execution of the neural network. Now, if you want to scale this, right, then the way this is done, right, is by connecting these GPUs together, right? And Google's view of this is the TPU pod, what Google describes as 100 petaflops of machine learning power. So this is the view of the hardware brain that we are now creating, where we started out with these, neuromorphic neurons in the beginning. So I'd like to examine this idea a little bit. So let's think about the compute that's involved in actual neural tissue, okay? And compare it to the amount of compute that we are, generating now with our beautiful TPU pods. So the human cortex has about 16 billion neurons. That's the number of neurons in your head, okay? And from energy considerations, we know that cortical neurons spike about, 0.16 times per second, okay? So based on that and knowing how many synapses each neuron has, we can kind of try to guess, right, how many, if we're trying to model, neurons in the same way that we have weights and connections in a neural network, then the 7,000 synapses probably connect us to maybe 700 or 70 connections per neuron. The reason I don't say that they connect us to 7,000 neurons is a picture like this. This is an image, for example, of a dendrite and an axon. The dendrite in green, the axon in blue. And you can see the synapses, the connections between the axon and the dendrite. And you can see that the axon is actually connecting in multiple places to the same dendrite. So in other words, the same neuron, if it connects, to another neuron with a synapse, it probably connects to it in many, many more other places. We don't know exactly how many, which is why instead of 7,000, I'm going to use 700 as the number of neurons that each neuron in cortex is connected to, but probably the number is closer to 70. So with that in mind, right, I take 16 billion times 0.16 times 700 connections is about, and assuming that every time that I fire, this thing, I am actually doing the same type of computation that I do in a neural network, then what I have is about 2 trillion operations per second, okay? So 2 trillion operations per second is like an iPhone, okay? It's not that much computation actually. And what this tells us is that the cortex, your cortex between your ears, what is going on there is 5 to 6 orders of magnitude less compute than the TPU pod, okay? Now, let's think of image recognition, which is a big thing we use neural networks for. So we typically take these 224 by 224 images, right? So 500,000 pixels, right? And we, a ResNet or some network like that will spend about 20 to 30 billion operations to compute on that, right? To compute on that image, okay? The human iris, okay, has 2,000x more pixels as input, okay? And so, a neural network to compute on the same kind of number of pixels that your iris does would take about 40 trillion operations, okay? And we recognize an image in 13 milliseconds, 100th of a second, as I showed you that picture of Mount Fuji. 13 milliseconds, you can tell what an image is, okay? So with that calculation, right, 2 trillion, let's say you use your whole brain for that calculation, times 0.13 is about 20 billion operations. So 20 billion, okay, compared to 40 trillion. So 3 to 4 orders of magnitude more efficient. That your brain is in recognizing images, we are 3 to 4 orders of magnitude more efficient than we are with neural networks the way they're executed right now. So that was compute. What about memory size? Well, you know, the human cortex has about 300 trillion synapses. Okay, if you think of that as a graph, just as a minimal representation of a graph, that comes out to be about a petabyte of memory. Okay, and the GPU typically, so your brain is about a petabyte of memory. The typical GPU or TPU, etc., has 16 to 32 gigs of HBM2 memory. So 16 gigs compared to a petabyte. So your brain is about a petabyte, and this is about 16 gigs, right? And even if you take a desktop, you have, you know, 1.4 terabytes on any desktop you can buy today. You can buy terabytes of memory. So very limited memory, right, on the GPUs or the TPUs, because you have to connect thousands of cores to the same, you know, kind of shared memory, and that kind of limits the scalability of your memory. So a GPU TPU pod, the thing that Google builds, right, is 4 to 5 orders of magnitude too small to actually hold the same amount of connectivity that your brain has, and if you were to represent a neural network of that size. So what is it that we're building? What is this brain in silicon that we're building right now, right? Well, what we're building, right, has a petaflop, right? We're trying to get a petaflop of compute and apply it to a cell phone of memory. While what our brain is, what we need if we want to mimic what we do in our brain, right, is to actually, you know, have a petabyte of memory and apply a cell phone of compute to it. Okay, so a cell phone of compute on a petabyte of memory is what we need, and what we're building is essentially the wrong thing, the exact opposite of what we need. And even if I'm wrong by a couple of orders of magnitude, it's still the same story. We aren't building what we need if what we want to mimic is the way our brain does things. And why? Why is this? Well, it's because we don't know the graph. We don't know the graph, and what I mean by that is we really don't know the computation, right? We don't know what the network needs to look like that does this kind of compute. But interestingly enough, we're learning, right? Machine learning is a very young field. It's been in existence really in its current form for about 10 years, maybe 12, right? And in this period of time, we've made incredible leaps in our understandings of what these networks should look like. Okay, we're nowhere near a complete understanding, right? Very far from it, but we're making progress. So here's an example of progress. This is from May 2019. Guys at Google came up with a network called EfficientNet. So I'm in this graph that you see here. I have, you know, on the X scale, you can see that I'm looking at the number of parameters that I need for a typical neural network, going all the way from small networks like small ResNets all the way to AmoebaNet. Okay, and I am looking at the accuracy that I get as I grow the size of the network, and you can see that, of course, AmoebaNet is much better than ResNet, you know, 50, for example, right? But here in red, right, are the EfficientNets, from EfficientNet B0 through EfficientNet B3, B4, up to EfficientNet B7. And what do we see here? Well, what we see here is, you know, that EfficientNet B0, a network that is the size of AmoebaNet, so, you know, 5 to 10x smaller than ResNet, okay, actually more than 10x smaller than ResNet, has the accuracy of ResNet, okay? If we look at EfficientNet B4, okay, it has the size of ResNet, okay, but the accuracy of AmoebaNet. So we're learning actually how to do it with much smaller networks, okay? So this is kind of, we're getting a better understanding of what's going on. And this translates also into compute. Here are some results that compare, you know, running EfficientNet B0 on, you know, on a GPU using MXNet, and on a CPU on AWS using the Neural Magic runtime. And what you can see is on the left side for batch size 1 inference, right? You can see that a 4-core CPU, okay, that costs 34 cents an hour, okay, is on the same order, a little better, than a Volta GPU that costs $3 an hour. Okay, that's for inference. But that's not that surprising because everybody will tell us that GPUs do better when they have larger batch size. Well, that's true, but here again, if you look at the right side of this, right, a $2 24-core Intel CPU will match the Volta. Okay, and if you want to use the same amount of money that the Volta costs, you can get 2x better than that if you just run 9 times 4 cores on Amazon for the same price. I guess what I'm trying to tell you is that, we're kind of with these new networks, we can match the performance of the GPUs. Okay, and here's another example, efficient at B4. This is the same accuracy as AmoebaNet, the largest networks that we have built before, right, to get accuracy. And here's what we're getting. We're getting, the same accuracy as AmoebaNet, right, using efficient at B4. A 24-core CPU is matching, batch size 1 is matching the Volta, and it's also the same ballpark, as the Volta, for high throughput case of batch 64. Okay, so these new networks, that our understanding of what neural networks do, right, is bringing us closer in accuracy to the larger networks with less compute. Now, given this, what is my view on where neural hardware is going? Okay, hardware and software. Well, here are some understandings from neurobiology about where we should be going. So there's a reason why there's, one of the things that was always said about neural networks is, oh, we need a lot of parallelism to do this computation. That's why we're building these accelerators, right? Because there's so much parallelism here. Okay, that's true, but why do we have parallelism in our brain? Okay, well, we have parallelism in our brain most likely because if you need to actually if you want to build something that does 1 billion operations per second and you're doing it from very slow chemical connections, that's what synapses are, then you need a lot of parallelism, okay? Because to get 1 billion instructions, you need 1 billion neurons, okay? But that doesn't mean that when I do this with silicon, I need to do the same thing. I can do 1 billion operations in silicon sequentially on a modern processor. A modern processor will do 10 billion operations per second. So I don't need parallelism, okay, in silicon in the same way that I needed it for doing this in the brain. And so, in other words, flops are flops are flops. If I can generate the flops sequentially or in parallel, I can still do the same calculation. I don't need parallelism if I can get the same flops sequentially. So that's one thing to learn, okay? So I don't need a massive parallel throughput computing device to actually compute a neural network fast. What I need is a certain number of flops, okay? And what can I learn about this computation from neural tissue? Well, I can learn 2 things. One is neural tissue is sparse, as I showed you, okay, extremely sparse, both in compute and layout. And neural tissue has locality of reference, okay? So these are the 2 things that I think we should take away from looking at brains, okay? And so this is what we need to mimic, right? Can we do this? Can we actually mimic sparsity and mimic locality of reference? So the answer is yes. Look, people are building all kinds of hardware, specialized hardware devices now that will actually bring the computation, okay, the compute into the, into close to the memory. There are hardware accelerators like that. I think NeuroBlade is an example of a company that is building an accelerator that actually does the computation on the memory. These are interesting things. But right now, when we still don't have those devices, maybe the easiest thing, the best thing to do is to do it on a CPU. And this is where Neural Magic comes in. That's what we do. We actually make a modern CPU, take all the learnings from neurobiology, and actually make it competitive with a GPU. How do we do this? Well, here's a comparison of the way computation unfolds on a CPU versus a GPU. So on a hardware accelerator, right, we have, here's our neural network in blue, right, described here, and we have, thousands of cores, each of them with a very small cache and with incredible bandwidth to memory. So bandwidth to memory is 10x more than a CPU, even more than that, right? So great bandwidth to memory, lots of cores, but tiny caches. A CPU, on the other hand, right, has few cores. They're powerful cores, very powerful cores, but fewer, right? And these cores have huge caches compared to the GPU, okay? 10x more cache. But then the kind of the bandwidth to memory is low. So bandwidth to memory is not as good as on the GPU. So one device has tiny caches, lots of bandwidth to memory. The other device is the CPU has lots of cache and not so great bandwidth to memory. Okay, so how do we do computation on these devices? Well, the typical way that you run in a hardware accelerator, right, is to execute synchronously layer after layer. And this is the beauty. This is Krzeszewski's great understanding that you can use the GPU to run through the layers of the neural network in parallel. So you read in a layer, compute on it, and write back the output and go from layer to layer to layer to layer, and you execute this synchronously layer after layer, and voila, the GPU is the perfect device for doing this, okay? Because you have so much bandwidth to memory, you don't have a problem bringing things in and out, and because you have so many cores, you're saturating them, and performance is fantastic. Now, what people try to do typically on a CPU is do the same thing. Okay, run depth-wise layer after layer, okay? And what happens when you do that is it works poorly. It works poorly for two reasons. First of all, because the networks that we have right now are compute intensive, and CPUs don't have the same amount of flops, right, as a GPU. And the other thing is, right, that I hit the memory bottleneck. Whenever I'm reading and writing and reading and writing from memory, the CPU has less bandwidth, and therefore it sucks in performance. So that's where we are, okay? So what Neural Magic does, okay, is we take that graph, okay, and without losing accuracy, as I have shown you, okay, we prune the network to reduce the compute. And pruning reduces the compute, keeps the, you can do that while keeping the accuracy within 1% away from what it was before. You can, sometimes it actually improves accuracy, pruning improves accuracy. And once you've done that, okay, then you're again in trouble, okay? And you're in trouble because the CPU doesn't have a lot of bandwidth to memory. You took something that was compute intensive and you made it memory bound. And so now again, we're in trouble, right? And we're in trouble because now, the CPU isn't as great as the GPU in terms of its memory boundedness, right? In terms of its ability to move things in and out of memory. So what Neural Magic does then, right, is we actually have a way of executing the computation asynchronously, mostly in cache. Okay, so we take this sparse computation and we run it essentially in the CPU's large caches. We make use of the fact that CPUs have really large caches, okay, and a good cache hierarchy and prefetching, okay, and we actually make use of that to run this sparse computation fast. And what do you get from that? Well, what you get from that is that, for example, if you look at ResNet 50, okay, a classical network that everybody uses, batch size 1, okay, a 24 core is, the same as a Volta, actually much better. Actually, you can get much better than these results, okay? But more interestingly, even in the place where supposedly the GPUs shine, right? The place where, the Volta is the device, right? Then again, the CPUs, at batch 64 match the performance of the of the GPUs. So what we're seeing is that the combination of sparsity and good use of locality of reference can actually, like in your brain, okay, in the same way, can actually match the computation in a neural network much better than these accelerators, okay? And because of that, we can get great performance at a lower price, and and we can do that with a lot of memory. CPUs have enormous amounts of memory available. You can put a terabyte on a desktop. You don't have to be limited by the size of the the accelerator's memory. So this is the software GPU. This is what Neural Magic makes. Our Neural Magic Engine 1.0, which is coming out of beta somewhere this summer, okay, makes sparsity easy. You sparsify your network and you can run it at GPU speeds, okay? And what this does, it enables you to run, big models on big inputs, things that don't fit in accelerator memory. It's software, so it's containerized, virtualized, move it anywhere you want. We don't care what you're running on. You don't need to know what you're running on, okay? And it eliminates all this added CapEx, OpEx, and DevEx of having special hardware in your data center, special hardware, in your, on the cloud. All this can go away because it's just software. And I'm not going to do a demo in this lecture, but at 1 o'clock today, there will be a live demo of our software, and whoever wants to join is welcome. And yeah, and with that, I'll say thank you, and I'm open to questions.
Hi, Nir, Sasha, you know me. I work with you on your marketing team, so I'll ask some questions that came through. So one of the questions is, how does quantum computing fit in this picture?
Okay, so quantum computing is an orthogonal approach to kind of optimizing computation. Right now, the way people view quantum computers is, a quantum computer is a way to actually efficiently solve what is otherwise an NP-complete problem efficiently. And so if you want to design a schedule, for example, you could use a quantum computer to just look at all the possible schedules and pick the optimal one. A neural network, right, is kind of orthogonal. What a neural network will do is very efficiently in kind of low polynomial time actually pick what is probably not the optimal solution, but is good enough. And so these are kind of two approaches perhaps to the same problem, right, but they don't achieve the same kind of result. One is looking for the optimum fast, and the other is looking for something that is close to the optimum fast. I hope that answers the question.
Cool. Just a reminder for everybody, there is a Q&A function here, so please ask your questions away. There's 2 more questions so far, but we probably have time to take more. Next question here. So your company, Neural Magic, you claim to execute deep learning on everyday CPUs while getting GPU class performance and better. So it sounds good to be true. What are we sacrificing, if anything, to get that performance?
So the process of actually preparing the networks to get the same performance right now involves actually running through a process of pruning and tuning. So this is similar to what people do to quantize the networks. So a similar process has to be done to sparsify. That is essentially the only overhead. And for that overhead of actually having the ML engineer have to do the pruning process, which by the way, our tools provide a semi-automatic way to do that. So you can either do it semi-automatically with our tools, or you can actually go ahead and handcraft your network even better to get better performance. But that is a thing that the engineer needs to do. But once he does that, then it's software. You don't have to have a GPU to run it. You can just run it on Intel, CPUs, and hopefully soon on AMD CPUs everywhere.
Yeah. No sacrifices in accuracy, right?
No, the accuracy sacrifices are on the same scale as those from quantization, which is becoming a standard technique in neural network deployment in inference. Yeah.
Got it. Another question from one of the attendees: is the dropout layer in neural networks different from this pruning method?
Yes. So the pruning process that's done here, and there are many variations of it, is during training, after you've trained your network to a certain degree, what you do is, for example, you drop all the connections that have that are below a certain weight. Okay, so close to zero. Let's say you drop the 50% lowest ones, and then you retrain the network again, and then you drop another percentage, and then you retrain again. So that's kind of different. It's a different kind of process, but it's a well-established process, and there's a lot of research going into that process. Yeah.
And then we have one more question. You can always ask more, but one more for now. What are the use cases you're able to fulfill with Neural Magic software?
So right now, Neural Magic provides recommendation system software and provides image classification, image object detection kind of software. And on our roadmap is to provide also segmentation and NLP in the form of transformers. That is coming down the road.
Awesome. I think that's it for questions. As Nir mentioned, we have a booth presence. Please swing by a booth to see a specific demo. We would love to show you a demo and walk you through the product. And also, we're holding a webinar, as you saw on Nir's screen, on May 5th. Come to our website, register. And with that, Nir, I'm going to leave it to you if you have any final words.
No, that's it. Thank you. Thank you, everybody, for listening.
Thank you, Nir. Thank you, Tasa, for such an interesting talk and taking the time to talk to the attendees and answer their questions. So just a brief, quick reminder, guys, just stick around for like a few seconds. There will be a short survey. And please give that short survey. Thank you. Bye.